Hello and welcome back to this online course on fundamentals of composites and cellular materials. So, we are discussing for last couple of classes, we are discussing about advanced composite materials. Okay. So, the plan in today's class is to continue in the same line, and in fact, if you remember that we classified the composite in terms of advanced composites in these 4 classes, and that is metal matrix composites, advanced MMCs, advanced CMCs, advanced processing techniques for composite materials, and then application oriented advanced composites. Okay. So, we are still continuing the first topic, that is advanced metal matrix composites. In the last class I gave 2 examples. In today's class I intend to provide 2 more examples on this particular topic of advanced metal matrix composites. So, let us begin. The first example in today's class which I want to give is copper SiC composite. Okay. Now, why copper SiC composite? Where is the application? The application is again electrical contacts where we need certain amount of wear resistance at higher temperature. Okay. So, and when we talk about this kind of metal matrix composite with ceramic reinforcement, the issue is the important challenge is basically how is the interface. Okay. And we have discussed in details about interface, but basically the points which you need to understand is that is there any mutual solubility between the matrix and reinforcement material. Okay. How is the weightability, that is very important, that the liquid metal or basically the metal matrix, is it weighting the ceramic surface, ceramic reinforcement surface properly or not. And another very important in this particular example is that reduction of thermal residual stress, during processing, it could be liquid phase it could be liquid phase processing, liquid state processing or solid state processing. In both cases, because of the elevated temperature processing, there will be residual stress. Okay. So, it should be as low as possible, because if there is residual stress, this residual stress could lead to cracking at the interface. So, we need to avoid residual stress generation as well. Now, in case of copper SiC composite, the advantage is that it combines high thermal and electrical conductivity with mechanical strength, moldability and low production cost. Now, copper gives very high thermal conductivity, electrical conductivity, and now if you want to improve the mechanical strength in terms of high temperature wear resistance, then you can think about reinforcing copper matrix with SiC particles. Okay. And as I mentioned earlier, the applications are in electrical contact materials, basically in relays, contactors, switches, circuit breakers, everywhere you can see that there is high temperature contact, okay, high temperature wear. Okay. And so the material should be withstanding that high temperature wear problem. Okay. Now, the major problem in case of copper silicon carbide composite is that the dissolution of silicon in copper matrix. That is the single most major or primary problem in this composite materials, that silicon from silicon carbide gets dissolved in copper and forms different kinds of harmful phases. Okay. So, as you can see here. So, the thing is that here liquid state processing, if it is possible, then we should avoid liquid state processing. Now, if we avoid liquid state processing, then the major problem would be the densification problem in terms of the interface will not be very adherent. If you go for solid state processing, weightability will be an issue, okay, because there is no liquid phase now. Okay. So, in this case, if you go for powder processing on the other hand, then silicon dissolution problem would be minimized, because there is no molten phase. So, silicon dissolution will be less. Okay. However, going for powder processing, so you have to think about better sintering. Okay. So, we can think about making this material by spark plasma sintering. And also if we go for powder processing, as I told that the wettability will be an issue. So, then this effect of metallic coating comes into picture. So, what has been done here, silicon carbide particles were coated with different kind of metallic thin films, and then those metal coated SiC particles were spark plasma sintered with copper particles, and then the effect of that metal coating has been observed in this particular example. Okay. That is basically the basic point in this particular case. So, you can see here there are three different kinds of metal coating has been done: tungsten, titanium and chromium coating. Okay. And the thickness of those coatings have been mentioned here. So, A, B and C after the coating, okay, and high magnification, you can see here there are three different coatings: tungsten coating, chromium coating and titanium coating. So, that is the coating the morphology of the thin film has been shown here, and these coatings have been done by physical vapor deposition, basically by sputtering technique. Okay. That means there will be a target of this elemental elements, and those targets will be sputtered, so that you create a vapor phase of these elements, and those vapor phase will ultimately get deposited on the SiC particles, and that will create a thin film, that will make a thin film on the SiC particles, thin film of the elemental powders, elements, tungsten, titanium and chromium. Okay. So, that is the basic idea, and once you make this coating of the on the SiC particles, then you mix with copper particles and then go for sintering. Okay. So, our aim here is to look at the interface in terms of wettability problem. So, before that the powder particles have been analyzed, and you can see here this is the SiC particle, only SiC peaks, but once you have tungsten coating or chromium coating or titanium coating, you can see those peaks, even the thin film, the films are quite thin, but still you can see peak for tungsten, chromium, okay, and titanium on the SiC particles. So, that means it has been deposited, and then you look at the interface, basically the surface of the basically the surface of the particles after the deposition of the different elements. So, you can see here the first one is uncoated SiC, and then you can see here. So, this side is basically the epoxy matrix in where the powder particles were actually sprinkled to get ultimately to look at SEM. So, these are individual powder particles after elemental deposition. So, the B is for tungsten coated, similarly chromium coated and titanium coated. So, at low magnification you do not really see much difference. You can see nice coating on the surface of these SiC particles in all cases. You can see here these coatings. Other than that, you are not really seeing anything. The main thing what you are seeing here is that nice uniform distribution or uniform deposition of the thin films. Okay. Let us look into a little bit high magnification how the interface is. Okay. So, the first one shows the, so this is the SiC particles, this side you have the copper matrix, and in between that you have this titanium coating. Okay. So, this is SiC particle was coated with titanium, and what you see here, the first thing you can see that the interface in both cases, both the sides are quite adherent. Okay. So, good titanium layer adhesion on SiC, and also you can see these black spots. These black spots are nothing but there is porosity on the titanium layer, and then you also can see here that these small white particles also, as you can see. Okay. At higher magnification you can see there are titanium grains which are basically nano grains, and then you see some white particles or white phase is also coming or appearing in the titanium layer. So, what you are seeing here is that the first thing you are seeing is that residual porosity in coating. So, you can see these black phases are basically the residual porosity. If you look at the dissolution, then you see silicon is not getting dissolved. So, the titanium layer is actually stopping the silicon dissolution very efficiently. Okay. However, if you look at this white particle, you can see basically this is basically the peak of titanium you are seeing, as well as you are seeing the peak of this green line is for titanium, sorry, and then the blue line is for copper. So, basically this is nothing but these white particles are nothing but titanium copper intermetallics Cu4Ti. Okay. So, across the layer what you see, there is no silicon dissolution, but copper, there is quite good amount of copper dissolution in titanium layer. However, at the end you can don't see in the SiC side or in the copper side there is no dissolution of silicon or no dissolution of copper. Okay. So, the dissolution of silicon can be restricted by titanium coating. However, you see there is porosity and there are some kind of intermetallic formation as well at the interface. Let us look into the next one, which is SiC copper chromium copper. That means one side is SiC and then you have copper, in between you have the chromium layer. That means the SiC particles now have been deposited with this chromium layer. Now, here you see the layer is quite complex in nature. That means, from this side to this side or from the copper side to this side, you see the morphology of the coating is actually changing, the microstructure of the coating is changing. What you see initially, basically at the outer layer of the coating, you see there is porosity, there are a lot of porosity is being present. Okay. And then in the second layer, what you are seeing is that there are columnar grains. Okay. You can see these columnar grains are there. Okay. And then in the third region also or third layer also, these columnar grains are there, but then these columnar grains are changing into this kind of equiax grains. So, in terms of grain morphology, you can see there is a fairly good variation from layer to layer. Okay. That is the first observation you can clearly see. In terms of dissolution, again you can see Si is not getting dissolved that much. Okay. There is some amount of dissolution of silicon is taking place here, but then you do not really see much of silicon dissolution in chromium in copper. That means, again the chromium coating is able to restrict silicon dissolution, which was the purpose. However, it forms this kind of complex microstructure. Okay. So, I have talked about this zone 1, zone 2, zone 3, zone 4 in terms of the morphology of the grains. What you also see in the zone 3, that means in this range, if you look at this mapping, okay, what you are seeing here, this line profile, what you are seeing here, that there is chromium dissolution, and also you are seeing in this particular case there is this silicon. So, that could be this kind of intermetallic formation, chromium silicon intermetallic formation. Similarly, some amount of copper is also, you can see this copper peaks. Okay. So, those could be certain amount of copper silicon intermetallic as well. Okay. Zone 4 says that good addition of chromium to SiC. Okay. So, that is not a problem, the addition or the dissolution restriction is not a problem, but then this microstructure is quite complex, there is a layered microstructure which is not very good in terms of mechanical property or thermal property. Okay. Now, let us look into the other one, the third one, where we have tungsten. Okay. Now, when you have tungsten, what you see here, there are certain amount of porosities you can see here. Okay. However, rather than except that, it is quite compact coating. Okay. And if you look at this, so it says more homogeneous and less porous than the other two. Some amount of residual porosity as you can see here, but that is quite less. Okay. Tungsten formed a continuous interface which consists of small equiaxial nanograins. So, these nanograins you can see here. Okay. All these nanograins you can clearly see. Okay. No penetration of silicon to the copper matrix and no copper beyond tungsten layer in contact with SiC. What does that mean? If you see in this elemental mapping, the line profile, you can see here this red one is for silicon and then the green one is for copper. So, silicon and copper both are going into the tungsten layer. However, beyond the tungsten layer, you can see silicon drops quite suddenly. Similarly, this green one which is copper, that is also quite false. I mean that there is a decrease in the resolution. That means there could be dissolution of silicon or copper in the tungsten thin film, but that is getting restricted there only. There is no dissolution of copper or silicon in silicon carbide or in copper matrix. That is what is most important. Okay. As I mentioned earlier, both copper and silicon presents in tungsten layer, reaction at the interface between silicon carbide and tungsten at temperatures up to 923 Kelvin. Okay. Now, let us look the finally, once we understand the microstructure at the interface, finally our aim was to understand the thermal conductivity. Okay. So, here in this graphs what have been shown that from A to B to C to D to E, SiC percentage is varying. So, here it is 5%, then 10%, then 15, 20 and 25%. So, different amount of silicon carbide reinforcement have been used in these 5 cases. Okay. Now, if you look at the first case where 5% silicon carbide and then you see these lines, all these lines are for different coatings. So, the first, so you can see here we have copper 5% SiC, that means this one, that is without any coating, and then with coatings the 3 different lines you can see. Okay. The first thing to notice here that with increasing temperature thermal conductivity is decreasing, okay, and that is going to happen anyway. That with increasing temperature thermal conductivity decreases. However, what is another important thing you can see here is that this line, which is basically for copper silicon carbide tungsten line, that means when the silicon carbide particles are coated with tungsten, that line is shown here, and in all cases you see this line is at the top. That means when you have tungsten deposited on SiC, thermal conductivity is the maximum. Why is that? Simply because if you look at this data here, thermal conductivity of tungsten is quite higher compared to the other elements like chromium or titanium. So, obviously, when you have coating of tungsten, that leads to better conductivity. That is understandable. In all cases you can see. Okay. Another thing what we are seeing here is that this gap between the tungsten line and the other lines is actually increasing with increase in silicon carbide percentage, amount of silicon carbide. Now, why is that thing happening? Anyone can have any idea? Okay, I will come to that, but another point you need to understand here also is that, so what is the data in case of 5% in the range of 340, if you talk about tungsten, 340, right. Then if you increase the SiC percentage, you can see it is going down 340 and then below 340, here it is around 320, here it is around 300 and here it is around 280. Okay. That means with increase in SiC percentage, obviously SiC is non-conductive. So, our thermal conductivity of SiC is low, I should not say non-conductive, but thermal conductivity of SiC is low. So, as you increase the SiC amount, thermal conductivity of the composite is going down. But what about this gap? This gap is increasing, and why this gap is increasing from as you increase the SiC percentage? Because now what is happening here, that SiC amount is increasing, that means the surface area, interfacial area is increasing from 5% to 25%, interfacial area is increasing. Now, this interface is covered with different kind of elements from tungsten to titanium to copper, chromium. Okay. Now, when the interface is covered with tungsten, that shows some improvement in conductivity, even if there is increase in SiC percentage, but still because of tungsten, the effect of tungsten, this gap is increasing. That in these cases, in these three cases, when you have chromium or when you have titanium, okay, thermal conductivity, the decrease in thermal conductivity is even more compared to tungsten, and that is why this gap is increasing as you increase, as there is increase in the SiC amount. Okay. So, this is the final thing I wanted to discuss about this particular example, is that how the thermal conductivity is varying with, there are 3 points here, with increase in SiC percentage and with change in the coating coating composition. Okay. So, I hope you understand this particular case here. The idea was to make a thin film on the surface of SiC particles, thin film, elemental thin film, to improve wettability and to improve to restrict the dissolution of silicon and copper in between interdissolution in intersolubility, to restrict the intersolubility of copper and silicon. Okay. And tungsten is most efficient in this case. Okay. So, now let us go to another example, and here you see that the composite material is carbon fiber reinforced magnesium composite. So, the matrix is magnesium and which is reinforced with carbon fiber, and it has been fabricated by a technique which I have not mentioned earlier, is liquid solid extrusion following vacuum pressure infiltration. We have heard about infiltration process, vacuum pressure infiltration. In this case, this is vacuum pressure infiltration only, however, it has been coupled with liquid solid extrusion. So, I will explain what exactly is this. In fact, for this particular processing technique, unique processing technique, I am giving you this particular example. So, magnesium alloy, as you can see, it will be definitely containing some amount of aluminum, okay, and zinc is there. Okay. Similarly, when you have carbon fiber, you can see because of carbon, carbon fiber has quite high strength in the range of 3.7 GPa. Modulus is quite high, that is why carbon fibers are used as reinforcement. And the application you can see here in the industrial application is to make crankshaft, connecting rod, gears, okay, all these applications are there for this particular material, magnesium composite reinforced with carbon fiber. All right. Now, what I want to show you is that the processing, how it is done. So, this processing is basically this liquid solid extrusion followed by vacuum pressure infiltration. Now, what is happening here? So, if you see here we have the liquid melt being prepared. So, here the magnesium alloy is being molten, and then by applying the vacuum pressure, this liquid melt is ejected towards this chamber. Now, what do we have in this chamber? Okay. So, the melting of the magnesium, so you can see here it is higher than the melting point in the range of 740 to 760 degrees Celsius, and then what do you have in this chamber? In the chamber you have a preform of the carbon fiber. The aim is to infiltrate or impregnate this carbon fiber preform. So, okay. So, now you can see the liquid goes here. The moment it enters the chamber, the temperature which has been maintained in this chamber is lower than the melting point. That means, once it enters this liquid molten metal enters into this chamber, the temperature is lowered and it becomes semi liquid. Okay. Now, what is the purpose of making this it semi liquid? Because if you decrease the temperature or if you make it semi liquid, then the viscosity increases, and if the viscosity increases, then this impregnation or the the infiltration process will be hampered, will be restricted, but still you are decreasing the temperature, you are what is happening, you are increasing the by decreasing the temperature, you are increasing the viscosity. Why? The only reason of reducing the temperature and going into semi-solid state or semi-liquid state is that to reduce the interfacial reaction at higher temperature, and also when you have liquid phase, the dissolution, the diffusion at the interface, the chemical reaction of the interface, all these things gets elevated. Those increases, the probability of those reactions or those dissolution would be increasing, and you want to restrict that. So, the temperature, even if there is problem in infiltration, but the temperature is minimized. But that problem of infiltration gets gets counter attacked by this extrusion press. Now, if there is an extrusion press which presses this semi liquid into the mold. So, that is why it says liquid solid extrusion. So, it is a like liquid solid phase which gets extruded inside the preform, okay, and that is why it is called liquid solid extrusion with vacuum press infiltration. Okay. So, it is basically amalgamation of two techniques. One is conventional vacuum infiltration, and then which is further enhanced, the infiltration process gets enhanced by this extrusion process. Okay. So, that is the basic processing technique here, and once it is done, the microstructures have been shown here that the fibers are relatively well distributed. You can see the fibers, those are relatively well distributed, and magnesium alloy embeds in the gaps among the fiber bundles, and no apparent porosity or significant casting defects are detected. Because of this pressure infiltration along with this extrusion, the porosity gets nicely filled, there is no defect. The defect is not coming because it is not completely liquid phase now. If you have liquid phase completely, there will be shrinkage defects, liquid solidification shrinkage defects and all those things, but those defects are also now you are avoiding by using this semi molten state alloy. So, there are certain advantages of going through a processing using semi molten state. First of all, the reaction temperature is less, so the reaction chance of reaction dissolution gets minimized. Okay. Secondly, it is not completely liquid state, so the casting defects or the solidification defects, the chance of having solidification defects also gets minimized. Okay. Now, let us look at the microstructure. So, fatigue study has been done on this particular composite material, okay. And before that you can see the tensile strength, tensile test also has been done. So, obviously, you can see if you compare the alloy, the tensile strength of the composite is quite high, in fact, it is more than double, okay, almost 3 times actually, and the modulus has also increased from 38 to 70. Obviously, when you are reinforcing with high strength fibers, the elongation is bound to go down. So, from 7.94 or from 8, it becomes 2.3. Okay. However, the fatigue limit improves. Okay. So, you can see here had highly fatigue resistance and never failed during fatigue loading at any number of fatigue cycles exceeding 10 to the power 4. So, the fatigue resistance of this composite material increases manifold once this kind of reinforcing by carbon fiber has been done in the matrix. Okay. And now, why is this, how actually the fatigue resistance improves, I mean the fatigue property improves. So, what happens actually as the fatigue loading is done, there will be this kind of crack generation at as you increase the fatigue cycle, number of fatigue cycle, that is, as you increase the stress or the loading, there will be, depending upon those two factors, there will be this kind of interfacial crack generation. Okay. And these interfacial cracks, however, these interfacial cracks are not through. Okay. So, there will be interfacial cracks and crack bridging. So, you can see this cracks is forming, okay, and then the crack is actually going through the interfaces at different stages, I mean different fibers. Okay. So, it is like a kind of never ending process. The crack is never through the material, okay, and that is the reason actually the fatigue resistance increases. So, what it says here, the fatigue process can cause interface weakening effect due to the interfacial debonding and sliding, which will result in fiber pull out or crack. That is what you are seeing here, that interfacial weakening effect is happening, and that leads to this kind of crack generation, this kind of fiber pull out, which you saw earlier, this fiber pull outs and crack generation. Okay. And the number of pull out fibers and cracks will be increasing definitely with increasing applied maximum load and fatigue cycles. That is bound to happen. However, this interface weakening effect actually has a positive effect on the properties of carbon fiber magnesium composite. I mean, properties means the fatigue resistance. Okay. So, the whole process gets delayed because of this tortuous path of crack propagation, and that leads to increase in the fatigue resistance. All right. So, with that, I would like to conclude today's class. In today's class, I discussed about two different examples. Again, both are metal matrix composites. In one case, it was copper SiC composite, and there we have seen the effect of metallic coating in order to restrict atomic dissolution, at the same time to improve wettability. So, what is the effect of metallic coating that we observed, and we observed that tungsten is giving the best result compared to chromium and titanium. And then the second example, it was basically a magnesium matrix composite which was reinforced with carbon fiber, and this has been fabricated by a novel technique which is called liquid solid extrusion with following by vacuum filtration, infiltration. Okay. And here we have observed that how the fatigue resistance or the fatigue property is increasing because of formation of, or basically because of the weakening of the interface, which leads to an enormous tortuous path of the crack. Okay. So, I conclude today's class, and in the next class, as I discussed about MMCs, advanced MMCs, in the next class my plan is to discuss on advanced composites where the matrix is ceramic. Okay. So, with that I conclude today's class. Thank you all.